So the next theorem we'll be talking about now is the theorem that angles in a circle, the angle that an arc of a circle subtends at the center is twice that which it subtends at any point on the remaining part of the circumference. So you'll be given a circle APB with center O. So you have to prove that AOB is twice of APB. So what this means is this. What I'm trying to say is this. Something like we'll be given a circle like this. Something like this. A circle APB. And the center of the circle is O. So we want to prove that this angle AOB is twice of angle APB. So now the first thing we'll do is we'll construct a line through O and P. So these are three different ways of drawing this, of proving this theorem. So in each of these cases, you can always draw a line through O. So if you like, you can make this APB widely. You can space the AP and B, or you can confine them here, or you can put them down, up or down. So each of the ways you draw the first one this way, the second one like a rectangle or parallelogram inside it. Then the third one is like opposite angles facing each other. So it will be like a cross. So but we'll be talking about this one now. So with the lettering, so this is the proof now. We've constructed our line from Q to O to P. Now OA is OP. So why is that? Because OA is the radius, right? And OP is also the radius. So these are equal radii. So that's the reason why OA is equal to OP. So the next thing is, therefore x1 is s2. This x1 will be x2. Why? Because that's base angles of an isosceles triangle. So base angles of an isosceles triangle are always equal. So that means therefore angle AOQ is x1 plus x2. Why is that? Because there's a theorem in mathematics that talks about exterior angle of a triangle. So this exterior angle AOQ, this AOQ is an exterior angle to this triangle AOP. So that means this exterior angle will be equal to the sum of the opposite interior angles. That will be x1 plus x2. That's what this one will be. So the next thing is AOQ will be 2x2. So why is that? AOQ will be 2x2 because x1 is x2. So that means AOQ will be x1 plus x2, and their x1 is x2. So that will be 2. That will be x1 plus x1, or x2 plus x2. That will be 2x2. So now, similarly, BOQ is 2y2. Like this one now, BOQ. If you analyze this second triangle, this y1 is equal to this y2 because that's base angles of this isosceles triangle. So that means this exterior angle because y1 plus y2, and that will be 2y2. So the next thing we will do is that now this AOB will be equal to what? This one here is 2x2 and this one is 2y2. So this total angle here will be 2x2 plus 2y2. That will be 2 open brackets x2 plus y2. That's why it's here. But this angle at the top is x2 plus y2. So and this one is 2x2 plus y2. That means this one is twice of this one, right? So that's how you prove this theory. So for further understanding, can reach out to me personally so that I can give you much more understanding on this topic. But this is the basics of how it works, and those are the proofs. But but it's rare that anybody will actually prove this. So the next thing we'll talk about now is angle in the same segment. So the angle in the same segments of a circle are equal. So what does this mean? That means this is the segment, something like this. This could be a segment. This. So this part of a circle, these angles are in the same segment. So if we have something like a chord now, here, this is a minor segment and this upward part will be this major segment. So that means these two angles are in the same segment because their bases, they are held by this same chord AB. So now that means this x1 will be equal to x2. But why is that? Let's prove that. AOB is 2x1, right? This one AOB will be 2x1. Because angle at the center of the circle is twice angle at the circumference, and AOB is 2x2. So if AOB is 2x1 and it's 2x2, that means x1 will be equal to x2. So that's why this angle APB is equal to angle AQB, and that proves that angle in the same segment of a circle are equal. So, and even this one, even if no matter how many angles there are, if this one, if there are 3 angles, there are 4 angles, there are 5 angles, as long as they are held by the same, they are the ends of this, the edges of the circle, the base edge are at the same point. Like this one, they all converge at this point. This one converge at this point. So any angle that proceeds from these 2 points will be equal to each other. And this one, all these 3 angles, x and this one and y and z, they all proceed from these 2 common points, and those 2 common points form a chord. So the first one I'm talking about now is angle in a semicircle. So the angle in a semicircle is the right angle. So the remaining theorems, they all stem out from the other one. Like this one now. This is a form of angle at the center is twice angle and circumference, because this angle at the center here is 180. So if we consider this one to be angle at the center, this angle here, AOB, that's 180, right? So that means the angle at the circumference will be half of AOB. That's half of AXB will be half of AOB, right? So that will be 180 over 2. That's why it's 90. So that means that's why the angle formed at the semicircle is 90 degrees. So this AXB will be 90 degrees. So the last one we're talking about today is the angle is cyclic quadrilaterals. Now the vertices of cyclic quadrilaterals lie on the circumference of the circle. So what that means is that these vertices, these points, they are the edges of, let's call them vertices rather, of this cyclic quadrilateral are on this circle, and it's called the